Thanks for keeping the class busy with announcements. Sorry, I'm a little late. So how was the exam? Was this exam clearer?
It was fun.
Yes. Why was it better? I'm trying to see what's the...
We got all the questions.
Okay.
I thought the objective questions as opposed to the true and false kind of made it a little more clear as to what we were looking for.
Okay.
But even these true and false made it a little more clear as to
Okay.
what kind of answers we're looking for.
Okay. Even the first time my intent was not just like a true or false except for the quiz, right? To give us stuff, but I'll try to have that, follow makes sense, follow the same model, right? So are there any questions about, so the homework assignment is due today, right? So if you pass it to the friends, that's fine. So are there any questions about what you covered so far? If not, I'll like to go through the atomic transactions, right? How many of you taken a course in databases so far? Few of you, right? So if you're taking a course in databases, this is it. I mean, the databases probably spend all the time talking about transactions and scalability and all those things, right? And we will go through them for for one lecture because it's an important concept. And there's a lot of push to move that into the OS kernel, even though, as you will see, it's a pretty expensive operation. It's pretty expensive to do some of this stuff, but it's a very powerful technique. So at the least, you will want to use it for programs and stuff. You'll definitely use it in databases, and there's a lot of push to move that into the kernel and so on, right? So the idea here is, when you operate on data structures, when you have threads and stuff, right? You're operating on a whole bunch of different fields, and if you're not careful, you may leave the stuff half done, right? So if you remember the, I'm going to erase this stuff. Yeah, talk to him, right? So OS basically has lots of tables that you move around, right? So for example, the process control block, when you're moving it from, say, waiting to ready state, right? Let's say this is a field called state. You change it to ready, right? You move it from one table to another one. So, for example, you may have a pointer pointing here, and pointer pointing to the next element in wait queue, right? You have to sort of move this pointer, make it point here, and move this into the other ready queue or whatever. So you're moving lots of pointers. You're moving it from one queue, moving it to another queue, making all these field changes and stuff, right? If halfway through something goes wrong, right, you're left in a weird state. So for example, if you change the state from waiting to ready, and then while you're doing some of the other processing, if something happens that you couldn't finish the stuff, right? So you could be left with a process control block which thinks it's ready while it's actually waiting, right? It could be at the waiting queue and so on, right? So you can have all this weird stuff, especially when you have multiple threads and multiple processors. So what you really want is, you want all the stuff that should happen. So in concept tree, you say, my process is done waiting for I/O. I want it to move from waiting to ready state. So all the programs and code I have to do, changing fields, changing pointers and stuff, all of them have to happen all at once on an atomic, right? And that's the notion of atomic transaction. You want to treat all of them, which may include many different operations and many different fields, right? It may involve changing fields, it may involve changing pointers on multiple queues. You want all of them to happen all at once on an atomic, right? And that's the notion of atomic transaction. And databases do this all the time. So, in this case, in database terminology, if you're trying to, let's say your checking account and savings account, right? If you're moving your money from savings account to a checking account, you want all of them to happen all at once and not at all, right? So you want the money to move from, you want the money to be deducted from your savings account, You want the money to be added to the checking account, and that's why you want to end, right? At the end of the transaction, you want your savings account to be reduced, your checking account to be increased, right? Maybe you don't really care if the savings account is reduced. You only care if your checking account. So if you had your savings account had $100, checking account had $0, right? At the end, you may want it to be 80, right? And you as the customer may not care if it happened to be like this, right? And the bank may not care if it is like this, right? But neither of those are acceptable. You want this to happen, right? So when it's trying to do this stuff, when you're trying to move the money from here to here, whatever has to happen, all has to happen, or nothing has to happen, right? And that's the notion of transactions. So databases live on this. This is the fundamental reason why you have a concept called database, pretty much, right? And so that's a similar step. So there are some terminology that you use, right? So when you go from, this is a transaction. A transaction is a set of operations, all of which together form some kind of a notion of what you're trying to do, right? And a committed transaction is we go from here to here, and everything is all set. That's considered to be committed, right? And if halfway through something happens and you have to back out, that's called an aborted transaction. And so if you're going through, when something weird is happening halfway through, you abort and go back to the starting state. So if you start from here, and while you are at this state, you notice some error, disk fails or a whole number of different events. You abort the transaction and you roll it back to the state that you were before, right? And so there's the concept of committed transaction where the transaction fully completes, abort a transaction where it's aborted, and you roll back to the state where you started, right? So you start from a state, you do a whole bunch of operations, try to finish all at once, and if it doesn't finish, you roll it back to where you were, right? And a good database would not let you see the middle values, right? While this transaction is going on, you won't be able to see these partial values because they are meaningless. You only want to see atomically from one to the other, right? And so one of the important ways you do this, you do the transaction, right, is you have to be able to implement the rollback. When something's going wrong, you want to be able to roll back. So the way you roll back is to use logs, right? So every time you do an operation, you log what you did. You log what the old value was, what you're trying to do, and you log them. And you have to save them in a stable state, right? So for example, if you're trying to, say, move $100 from here to here, right? So you have to say, first, let's say this is a transaction, right? So let's say this is transaction T1, right? And I'm going to make S, right? Old value used to be 100, new value is 80, right? I'm going to do transaction 1, C, old value is 0, 20. Okay. I can say start T, right? And then T. So I write down everything I'm doing, because if I ever get to this point commit, which means that the whole transaction was completed, then I don't have to remember all this stuff, right? But if things had to fail in the middle, I should go back to where the state is. I can replay the whole state back because I know what the new value that I put, what the old value is, so I can roll back by going back, right? So I note down everything I've done so far, so I use that to roll back to where I have to go back, right? So that's a traditional way you deal with the transactions. So every time you make a change, you say you write these things. You say I'm going to start a transaction, and I keep writing what I've changed, and then when I'm done, I roll back, right? And as with the whole notion of threads and all those things, the notion of transaction is up to you as a programmer to define what it is. So there's no notion, there's no magical way to create this stuff. You as a programmer have to know what is a transaction. So you have to know when it starts and when it ends, right? So you have to know, I'm going to do this operation, so I'm going to start a transaction, right? So you can have support to create these logs and stuff, but essentially you have to figure out when the transaction starts, when the transaction ends. And you write all this stuff, right? So this must be pretty obvious to the folks who were doing databases, right? And if you haven't taken database, if you're taking database in the future, this is database 101 kind of stuff, and you start from there, right? And the logs are considered to be idempotent because you can always roll back and forward. So any database can roll back and you can roll forward. Basically, if you keep keeping these logs forever, right, at any time you can actually go back to where you started by essentially reverting everything back, right? All the variables can be rolled back to where the state is and then roll forward. And a little bit we'll see why you want to do roll back and roll forward. Essentially, logs let you go forward and backward. And we'll see logs used in a different context when we talk about file systems. Right? When we talk about file systems, which is the two models from now, essentially you want to use this concept of logs to make sure that you know what, if you're part of a transaction, you can roll back, right? And that's the one that protects you when you pull the plug off your machine, you can this one up again.
The logs you talk about here, are they going to be maintained, in the future on the machine, or do they just get overwritten?
So that's exactly what I think the next slide will talk about that, right? So in the conceptual sense, the logs are kept forever. Conceptual logs are kept forever, and the log you depend on the logs. If the log gets corrupted, if the log gets overwritten, then you can't roll back, right? So you have to have a notion of stable storage, like this concept of a stable storage, where whatever you write has to be stored, has to be there, right? And in real machines, that may or may not happen, right? I mean, we know disks fail, we know things fail. So for the most part, you have to define what is meant by stable storage for your context, right? In a database construct, databases go through a lot of hassle to make sure that the stable storage is stable, right? So they have to worry about disk crashing, because if the disk crashes, they'll just go away. That's happening, right? For operating system, if you're using within operating system, it's not so important, right? Because if the machine was to, in this case, this has to be stable, right? I mean, you want your bank account to, you either want this or this, but you don't want this to happen as a customer, right? Whereas in operating system, when I'm talking about that, filling runtable and all those things, right? Suppose you store it in your main memory, right? And suppose you put the plug, means the log is gone, right? Is that a problem if the log is lost in that context? So you're operating on a PCB, right? And you're trying to operate on changing the state from wait to, let's say, running, right? And you're logging all these operations, and somebody pulled the plug, and you lost all the logs, right? Yeah.
It's not really a big deal if you have to restart it.
Yeah, in that case, even the PCB is gone, right? The whole thing is gone. So you don't really care about these logs once you reboot the machine. Because once you reboot the machine, it's all new, you're getting a new process, new state and everything. So you don't really care about keeping it across reboots, right? So you can get away with like this logs not being really stable. I mean, it has to be stable while the operating system is running. But if it crashed, then the log is gone. That's fine, right? We still have to address the issue of what happens if the log keeps growing. Because the way I talked about, the next one you have to say start transaction and keep going, right? So your logs will keep growing forever, but within the operating system, you don't actually have to put it in a stable storage, right? You can leave it in the main memory, because if the machine crashes, you're okay. And as we will see, that's not true for file systems, right? If any of you have used a DOS machine, right? If you pull the plug, if you had to reboot the machine halfway through, you'll go through a scan disk every time you reboot the machine, right? And that's because all these structures were not fully flushed, were not fully taken care. So it has to go back and clean all the stuff, right? If you notice, most of your modern machines, one of the messages it will say is replaying the log, right? Because it keeps logging on. We'll get to this in the module following this. But in the case of the file system, all the files that you're storing they survive crashes, right? So the logs there have to be really in a stable storage. But within the OS kernel, if you want to implement this, you have to worry about the stable storage. So if in the real case, the logs will keep growing forever, and you don't have resources to store logs all the time. So you have a notion of a checkpoint, which basically says that at this point, I've done all the stuff, I've done all the commits, I've done all the transactions. So I know from this point on, everything is where they should be, and then I go forward from that, right? Your banks do that, if you have credit cards, weekend, some nights and stuff, it's not available at some time. Somebody made a notice that on Saturday night, they run this run, right? So they go through all the transactions, they clear out all the transactions. At some point they say, we have checkpointed, so we believe that no transaction from before should come here, and this is a stable state, right? And we move forward from that point, right? And again, you have to define what the checkpoint point is. And in the next slide, I'll see where the problems for all these things come from, right? For a single thread, this is not a big deal. When things get interesting, we have multiple threads. Right? So essentially, at some point, you would say, I know everything up till this point is clear, right? So I do a checkpoint, I write this on the log, and I keep everything beyond that, right? When you have to replay, I can go back to the checkpoint and then start replaying from that point. Right? And this is more of a thing you do for file systems, it's more of a thing you do for databases, not necessarily for operating systems. Yeah.
So when you do a checkpoint, you are flushing the logs that are in volatile storage and you're doing single storage, is that right?
In the case of operating system, when you do a checkpoint, essentially you're saying all the transactions I'm happy with, right? In the case of a database, you're saying I know it's actually on the hard disk, it's stored on the hard disk, everything is fine. Kind of stuff, right? And if you take databases, that's not a trivial task to flush everything to hard disk, right? Because you can flush it to the hard disk and it still takes a while and all those things. And we'll see a little bit of that later on, right?
So in an operating system situation, you don't need to like save these logs?
You at some point you can say checkpoint and then move on. Yeah. And a lot of operating systems don't do many of this stuff, right? And the reason why they don't do this is it's just kind of complicated to do all this stuff, and they kind of get away with not dealing with this, right? And I'll show you next slide why all this complication comes in, and it's actually a lot more complicated than what we've seen so far, right? You have to have a notion of serializable transactions, right? And the way to avoid that is to make the OS single-threaded, right? Because if you're single-threaded, none of this will happen. It's a lot easier to roll back and roll forward and stuff like that. Very few operating systems are really multi-threaded within the operating system, right? So they get away with not having to deal with many of this stuff, right? But I'm not sure if Vista actually does that, but they're supposed to do that with the Vista. Microsoft promised a whole bunch of stuff, and then they kind of pulled back on a whole bunch of stuff what they were going to do. So I'm not sure what they exactly ended up doing. Right? So the real interesting stuff happens when you have these transactions happening on multiple threads, right? So suppose you have one thread doing this stuff. You're operating on your bank account on one thread, right? You're operating on, one thread is operating on my bank account, one thread is operating on your bank account, right? That's safe, right? I mean, that doesn't really matter because let's say it's operating on savings account 1 is doing some operation. It's doing some operation on savings account, checking account for user 1, and for the second user, it's doing something, and so on, right? So in this case, since these are two different variables, there is no real cause for conflict. So suppose this was operating on 2, right? So this means that again, you have the same issue of what we're looking about, like in terms of shared code, right? So here you're operating on the same account on both these transactions, right? The atomic transaction notion means that either this all should happen at once or this all should happen at once. You're not allowed to have these things operate halfway through, right? And you can imagine what will happen. So if you're moving some account, so suppose this was checking and saving, right? So suppose you move some money from savings to checking, and then you're moving money from checking to saving, right? So let's say you went to the bank and this is savings, this is checking, right? It used to be like this, right? And you moved, let's say, $80, so this becomes like this, right? And a second later, you decide this is not what you want to do, so you move it back here, right? So you moved $80 from your savings to checking, and then a second later you moved it from here to here, right? So this means that you first have to take the money from savings and move it to checking, right? And then move from checking to savings. So they all have to happen in that order, right? So it has to happen that, so if you do this first, right? If you try to do this operation first, that means you're trying to move money from your checking to saving, right? When you start out, this money was 0, so you'll end up with minus 80 and 180. Right? If you did this first, you'll end up with something like this, right? Worse, if they were interleaved, things will go really bad, right? This is very similar to the notion of the shared variables and stuff. You're trying to do a transaction, right? You want stuff to happen at a certain order, and if they halfway through the interleaved and stuff, things go wrong. So if you have two transactions operating on the same variable, you have to do something. So that's the notion of a serial schedule, right? So what a serial schedule says that is, if you have a lot of transactions, serial schedule says that they all happen in some serial fashion, right? Serial meaning, so if you have transaction 1 and 2, right? A serial schedule is T1, T2, or T2, T1, right? So the example I talked about is more stricter than what we're talking about here. In a serial schedule, you say there's a lot of transactions. There's any number of different serial ways of doing that. You don't actually specify which way it happens, but it has to happen serially, right? So if you have transactions T1, T2, T3, right? The possible values are T1 followed by T2 followed by T3, right? You can have T2 followed by T1 followed by T3. You cannot have T1, T2 at the same time, T3, right? This is not serial. This is serial, right? And this basically says that one happens and then the next happens and the next happens. It does not say which one has to happen first, which one has to happen next, which one has to happen following. These transactions cannot be happening in parallel, right? Because if they happen in parallel, then it's possible that they're operating on the, they're reading the same values which are only fact modified. Yeah.
Is there some sort of scheduling algorithm, like if in that case, when one operation needs to be done before another, is there sort of algorithm for that? Or?
It's up to you to implement that.
Okay.
In the general case, you don't worry about those. In the general case, first you try to get this concept going, right? You try to make sure that only one transaction can go through, right? But if your application really needs this semantics where only one of those schedules is useful to you, it's up to you to implement that concept, right? But in general, transactions cannot happen like this, right? There's no feasible way where this should happen, right? So in the case of the, let's go back to the case of the changing states, right? Suppose you have thread 1, and its goal is to change a process from wait to ready, right? And suppose this process 2, which is changing a process from ready to run or something, right? So with these transactions, either T1 should happen and then T2, right? It's okay from a transaction perspective that this happens, right? But it's not okay to be happening at the same time, because if they're happening at the same time, then your pointers are all like still half done, so you can't let that happen. And again, in this context, it doesn't make sense to make it T2, T1 because the status hasn't even changed, but that's up to the user to change those stuff. So if you fully implement it as serial schedule, if you only let one transaction go at a time, right, that's a very slow operation. So you conceptually want this to happen, but you may not practically want that to happen, right? So because if you practically make that happen, every transaction, only one transaction can go through, right? So for example, in this case, we have to protect it because they are operating on the same variable. But if they're operating in different variables, there's no reason why these transactions should be happening at the same time. So use that notion. So use notion that if two transactions are operating on different variables, then they can go in parallel, because then you can use all the processes you have. But if they're all operating on the same variable, then you want them to go sequentially, right? And so that's the notion we'll see next. So the notion of the serializability says that I can serialize it to any, if you give me a bunch of transactions, I can give you some serial order, right? Where one happens after the other. I cannot make them happen parallelly. So, but doing that is slow, especially when they're not sharing any variable, right? So we define the notion when you have, if you're operating on the same data item, that's called a conflict, right? If two transactions are operating on the same data variable, that's a conflict, and we'll do something about it. If two transactions are operating on different variables, then they can both go at the same time. So you can still do T2, T1 at the same time, but conceptually it's the same as T1, T2 or T2, T1, because you don't actually make any effect with conflicts. Does that make sense? You don't want this to happen, right? T2 and T1 happen at the same time because potentially they could both be operating on the same set of variables and bad things can happen. But somehow if you figure out that they're not operating on the same variable, right, then I can actually make these two go in parallel, and you won't be able to tell the difference because even though they're going in parallel, they're not operating on the same variable. I think I have an example in a slide I told to show what that means. Right? So you define the notion of a conflict and say, if things are conflicting, then they can't go in parallel. If things are not going conflicting, then they have to go sequentially one after the other. Next. So here's an example of, so over here is a series. So there are two transactions, one in blue, one in gold, right? And there are two different ways of scheduling them. One is the gray bar and one is the white background, right? So the first transaction goes to read something from variable A, write something, read something in variable B, write something. The second one does this transaction, right? A serial transaction would mean that one should happen after the other one, right? So you have that read, either transaction one finishes, the blue one finishes, and then the gold one goes, or the gold one finishes, and then the blue one goes. So that's a serial schedule. That's that has the some database properties, right? But if you want to get these things going in parallel, right, you introduce the notion of a conflict serializable, which basically says that unless there's a conflict, they can both go in parallel. So if you're operating on two different variables, they can go in parallel. If you're operating on if you're not modifying something, they can go in parallel, right? So let's see why this is conflict serializable, right? The second case, right? The way you do that is you try to move them around to see if you can get from here to that, right? I'm kind of going through this really fast because this is a lot of stuff you see in databases, right? So for folks who went to databases course, it probably would have taken a while to go through these concepts, right? And it's not really fundamental to the operating system. It's a nice technique, so I'm kind of going through them fast. And if you
we didn't go through these in databases, but
you did?
We think like a lot of us kind of had an idea of this, I haven't done that, but we didn't go over the specifics.
But databases, that's the main stuff they do, right?
We like learn MySQL or SQL or something like that, basically.
Okay. Because, okay, underneath MySQL, right, databases is all about transactions, right? If databases are not transactions, if databases are operating on data, then they're not in program, right? The thing which differentiates databases from writing your own spaghetti code is that databases give you this very strong guarantees. They give you a transaction. So when you do MySQL is a way to interact with the database, right? But when you say select something, actually insert something, or modify something, right? That operation will make everything happen all at once and none at all, right? And you might have used the abort concept in your transaction, right? When you say, transaction abort, do some procedure, right? Okay. Anyway, so you should have, this is the fundamental database concept you should have learned in databases, and I'm not sure why you didn't get to cover it, right? So anyway, so let's look at this one, right? So you have the A. So these are, hopefully two different threads which are doing this stuff, right? So what we do is let's look at these two operations, right? This is operating on variable B. This is operating on variable A, right? Which means that you can run them in any order. You won't notice any conflict, right? So I can actually run this as I can move right A here and B here, right? I can do this and it's still you won't notice the difference, right? And again here and here, right? Which means this is operating on different variable, this is operating on different variable. So I can actually run it here like this and here like this, right? And you can do the same thing here, look at this and this operating on A, this is operating on B. So I can make like B up here, right here, here. If you move it like this, eventually you get back to that schedule, right? So even though they are running in parallel, since they're operating on different variables, since I can move this stuff around, I can go from here to there. So I can get a serial schedule out of this stuff without noticing any conflict, right? If it happened that both the reader, if there's no B and all of them operating on A and B, right, you couldn't do this, right? Because so all the transaction has to finish. You won't be able to move this around. So this particular transaction would be illegal, right? So what I mean is, if you had the A, right A, the A, right A, the A. If this is how it was being done, right? You can't move this around because whatever you wrote here would affect something here, right? So this particular transaction cannot be interleaved like this. This particular transaction has to only run like that, right? It cannot be interleaved like this. So if you're operating on the same variable, those two transactions have to be serial. If they're not, so you cannot find a conflict serializable way to move from here to there, so it's illegal. Right? Does that make sense? Essentially, you're trying to say, conceptually, this is what I want to achieve, right? Is there a way I can do this parallelly and still make it look like I'm there, right? If you do like this, there is no way you can make it look like that, because that says you have to do the read A, write A, read A, write A, and then read A, write A, read A, write A, right? So whatever was left over from the last write is what should be read by the first go. And if you do like this, that's not true. You're not sending this. So you really want this value of write to go here, right? So this has to happen before this happens, right? And that's not true. Right? So these concepts are some of the stuff that makes that why OS people don't like to do this inside the kernel, right? You have to make sure that all this is serializable, all those things. In a database concept, underneath, within your database, they have to, I mean, this is the brains of what the databases do, right? When you use it, you can use select and all those queries and stuff, and it's all fine. But underneath, they have to be able to do all this stuff. Whereas an operating system is the one which has to do this stuff, right? And for the most part, people get away with it, and they're fine, right? So what will happen? So one of the ways I said, you can solve with this is to have only the OS being single threaded, right? What happens when you go to like the 80 core processor, right? Let's say in 10 years you have 80 core processor. Can you get away with not doing it parallel? Yeah. So one argument would be, yeah, you're wasting the OS. I mean, you're wasting all the processors. You have a lot of stuff to do, then you're wasting the processor. The other argument is OS should not be doing a whole bunch of stuff anyway. I mean, whatever OS does is overhead, right? From your perspective, you're trying to get your work done. You don't really care what the OS does. So you really want the OS to do practically nothing, right? So you don't really care about these arguments and stuff. I think you can take it to some extent. I don't think you can take it to 80 core, right? I think you can take it to 2 core. You can say, OS shouldn't do that much. We can get away with the serial stuff.
Yeah.
But you won't be able to get away with that for a while, right? And again, I'm just going to say these things. Unfortunately, it should have been covered in the database class. But so one of the main things that they use for ensuring certain order, like what we are talking about, is called two-phase commit protocol, right? A two-phase commit protocol is one of the basic stuff in databases, right? So we'll get back to that a little bit here, but it's mostly a database concept. So the way you achieve certain this ordering is to acquire the locks for the transaction in certain orders, right? So you go through in the two-phase protocol, you go through a growing phase and a shrinking phase. Essentially, you go through and acquire all the locks that you need for the transaction before releasing them, right? So in the case, like here you would have wanted a lock for A, you would have wanted a lock for B, right? Two-phase commit protocol, before you start the transaction, you acquire the lock for A, acquire the lock for B, acquire all the locks that you need for the transaction before you give away stuff, right? You don't lock them as they, so when you write the code with the sum of force and stuff, right? You could have said lock A, lock B, right? The example behind on the board was like this, right? Yeah, so you could have said lock B and made this happen. Right? When you're writing a code, you could have said, I'm going to use A now, so I'm going to lock A. I'm going to use B now, so I'm going to lock B, right? Which is how you would have program for your programming project. You can't do that because you can prove doing this would not get you context serializability, right? And the way to achieve that is to have growing phase where up here you have to say, I want lock A, lock B, and then move forward. Right? I'm not going to any of these details because the theory behind it is horrendous, but trust me, these things work. Right? It's horrendous because that's database, right? And I would guess that you would have spent like half a semester on trying to understand why these are, what context serializability means, what before, after, logical process, all those things are. Right? But for now, the big concept is, what I want you to take away from this is, within your kernel, you want to do this operation. Within your program, you want to do these things in a certain serial order, right? But since you're operating on many variables, you have to have a notion of transaction, otherwise you are left in some weird state. Right? If you're operating on some of the state, you have to have a notion of a transaction, right? If you didn't, whenever you have to abort, you have to be able to undo all the changes you did. Like otherwise your program would behave poorly. And it's more important for the kernel because within the kernel, it's operating on a lot of tables. So if it didn't finish some of the tables, if you left them halfway through, that is catastrophic, right? And transactions are a good way, but to do that, it's not a trivial, you don't just lock and stuff. You have to have certain locking primitives, sort of like the two-phase commit protocol, or there's a time-based protocol. I'm not going to go through them again in class, especially since it's kind of involved. Right? So essentially, you use a time to figure out which should happen before what. Right? I'll try to go through them a little bit in next class, we kind of out of time. But more details, if anyone is interested, I can go through them. But we'll go through a little bit of this and go to deadlock in the next lecture.